Hi everyone, the central limit theorem is a weak convergence theorem. It states that the centralized and normalized sum of IID random variables converges in distribution or weakly to standard normal. Hence we need to take a careful look on weak convergence, and we're going to combine that with characteristic functions to eventually prove the central limit theorem. I would like to start with reminding you to the definition of weak convergence. So we have a sequence of random variables converging weakly if for any bounded continuous functions the expectations of those test functions converge. Equivalently, if the distribution functions converge at all points of continuity of the limit distribution. And we're going to look at this one more. Okay, so we want the convergence of the distribution functions. I would also like to remind you to this notational remark which we had before, namely a distribution function is unique to a measure on the real numbers by essentially the Lebesgue-Thirtieth measure, which is defined by the measure of AB being the increment of the distribution function over that interval. So I'm going to use these two interchangeably, so distribution function and measure will be the same thing, connected by this connection. So that's just some preliminaries. Let me start off with an example. So an example of weak convergence, it's supposed to tell you what can go wrong and why we need to look at all the things we are going to look at. Okay, it's a very simple example. Take a distribution function fn of x, which is extremely simple. It has to be continuous from the right, and so it's going to have a jump at n. It jumps from 0 to 1 at n. It's a very simple function. In fact, it's a very simple distribution because it just tells you that x is equal to n with probability 1. But in fact, what I did is a distribution function for all n's. So what happens to these distribution functions as n goes to infinity? And the answer is that as n goes to infinity, the jump position is pulled off to the right, infinitely far. And for any fixed point x, if I fixed any point x, then eventually this jump point will pull over x. And for any fixed point, the limit of these functions is 0. Now, is the identically 0 function, is that a distribution function? And the answer is no, it's not. This thing is not a cumulative distribution function, and these are exactly the issues we need to address. The limit of distribution functions might not be a distribution function itself, and this is where things can go wrong. So we have to address this problem, and this is what we're going to work for in the next couple of videos and a couple of lectures, if you wish. Okay, I need to make two definitions for now. The first definition is about relative compactness. So suppose I'm given a family of distributions, which I'm going to denote by P. And by distributions, I always understand distributions on R. So these measures mu on R, which are one-to-one with the distribution functions. Family P of distributions is relatively compact. Relatively compact if the following is true: every sequence mu n in P has a subsequence that weakly converges to a probability distribution, to a distribution. Okay, Notice that this example here, Fn does not satisfy this, because the distribution functions weakly converge to the identically zero function, which is not a probability distribution. And therefore every subsequence also converges to the same zero, which is not a probability distribution. The problem is that we're losing some kind of a compactness here, and this definition is exactly to capture that, what we're losing here. So the family of distribution is relatively compact if every sequence in mu has a subsequence that converges to a distribution, not to zero, but to a distribution. This distribution does not necessarily need to be in P. So this distribution can be outside the family we started with, but it still has to be a distribution. Okay, that's the first definition I want to make. And this definition, I hope everybody understands that this addresses the problem we had before, at least on the level of definitions. The second definition I want to make is the following. A sequence mu n is tight if for every positive epsilon there exists k, a subset of R, k, which is compact. In R, these are just closed and bounded sets, such that, or and, there exists a k which is compact, and if I take the following object, take mu n of all R minus the compact set, and take a supremum in n, then this is still smaller than epsilon. Okay, that's tightness. Okay, now again notice that this example is not tight. In this example the mass is 1 at n. So if I want the mass, so what is this statement about? Take any small epsilon, then you can find a compact, in other words, closed and bounded set. Bound is the most important statement here. So a bounded set such that the weight outside your bounded set is uniformly smaller than epsilon. For every measure is smaller than epsilon. Obviously in this example, if I try to pick any compact set, any say compact interval, then eventually the weight will escape this compact interval, and the weight outside the compact interval will eventually be 1, so this supremum is 1, so that example is not tight. So that's another kind of definition which tries to capture what's going wrong in that example. What we are going to work towards is to show that these two are actually the same. So that will be an important step in proving the central limit theorem.